3. Let's do it 0, 3. Why this is not allowed? All right. So, all right. Last time we saw the definitions of asymptotic upper bounds, lower bounds, and tight bounds. And this time we'll move forward and we'll go to graphs. But before that, I wanted to do just a small survey like they do in the book of common running times. Okay, so just a moment. So any questions or doubts from last lecture till then? Okay. Yeah. So let's just do a quick survey. We have seen like most of the running times, but let's see some common running times that we'll encounter during the course. Okay. So first one is linear time. Okay, which is big O of n, right? And tell me some algorithm which has order of n running time.
Finding max.
Yeah, max, min, and then let's say sorting two or merging two sorted lists. These you must have seen in your data structures and algorithms course. So still, just to repeat, like if you have two sorted lists and you want to merge them in a big list, then you just keep a pointer in the first list, in the second list, compare these two numbers, and whichever is smaller you put there, and whichever is smaller you move that pointer ahead. Then you compare these two numbers, whichever is smaller you put here. So the total time taken is this list length plus this list length, which is linear. Okay, anyway, I was just repeating that for the sake of it. Then we have order and log n time, which might seem a bit artificial, but this is very essential in sorting algorithms, right? And this is in fact a worst case lowered bound. For sorting. Okay. So again, you might have seen that for sorting, like quick sort, and there are some others which run in either order n log n expected time or order n log n worst case time. Okay. Then we have quadratic time. So this is also very common. So one example that the book gives, and I'll just repeat it, but this is not the worst case for this problem, is you are given n points on a plane, a two-dimensional plane, okay? And you want to find pair of points which are closest. Closest to each other. So what is the brute force algorithm? It's trying all.
Each pair of points.
Yeah, try all and choose two pairs, and find their distance and find the minimum of this. And this takes order n square time, because n choose 2 is n minus 1 over 2 is theta n square. Good. Then we also have cubic time, which is a bit more rare, but there's an example which a very natural example where we see cubic times is that suppose you are given like n sets of subsets of 1 to n. So there is like n is getting overloaded, but it is deliberately that the n is the same. And what are the n sets? Let's say S1 to Sn. And you want to find if there are two that are disjoint. Okay. So how would you do that? How many pairs of sets are there? And choose two pairs of sets. And for each pair, you look at each element to be in the intersection. If it is in the intersection, then you say that they are not disjoint. So what is the running time? M choose 2 times n. Okay, is equal to order n cube. And then we have some exponential times, not necessarily exponential because the first one is polynomial for fixed k. So n to the k time, let's say k is fixed. So suppose you are asked, so you have done, so discrete math is a prerequisite, right? So you know what are graphs, and I'll be coming to graphs again. So you know what is an independent set. So question is to find independent set of size k. Find if there exists an independent set of size k. Okay. So n choose k sets if n is the number of vertices in the graph. So n choose k subsets of size exactly k, and for each of them, you find out whether they are independent or not. So n choose k times some, let's say n square. No, n choose k times, and then yeah. So it might be n to the k plus 1 or something because of for each set you might need to find out whether they actually form an independent set or not. But this is like roughly the same. So you get this is order n to the k. Good. Then we have 2 to the n time. So any guesses where this can occur?
Checking all the subsets of a given set.
Yeah, exactly. So and any example where that might need to happen?
Find all the subsets whose sum is equal to a given number k.
Yeah, something like that. Exactly. So you are given a set.
Traveling sales.
Traveling salesman, yeah. A traveling salesman is not for subsets, right? Okay, depends on the problem. So traveling salesman has many formulations. So let's not worry about that. But this one is given a set. Find if any subset sums to a given number. Okay, so this will take to the n subsets. For each of them, you will take polynomial time or some time, and that is fine. So again, like there might be something else here, but 2 to the n time is going to be. And then what else? There can be, okay, in graphs. So instead of you are asked whether there exists an independent set of size k, you are asked find the largest independent set. Then you might have to go through all the sets. So okay, so for this you might have to go through, or brute force algorithm in worst case will go through all the sets. Force all subsets.
by independent set, you mean like a connected component in a graph or what?
No, so you should revise some of the, or I don't know if it was not taught, but I'll try to repeat those things from graph theory, but I'll not be going very deep. So independent set is just a set of vertices such that there no pair of them is connected, like no two of them are connected. So it's like complement of complete graph.
Okay, basically like the opposite of a connected graph.
Opposite of a complete graph.
Okay.
So these two are different things: complete graph and connected graph, right? Like a path is connected, but it's not complete. Okay.
Yes, sir. Thank you.
And then we have n factorial time. Finally, and I don't think we'll be going above n factorial in this course. Even n factorial, I don't think, or maybe we'll see. So if you have a bipartite graph, a complete bipartite graph with n vertices on each side. So this is suppose a complete bipartite graph, all the edges are present. And suppose the whatever, like all the edges are weighted. So they have some weights. And then you are asked find the minimum weight, maximum matching or perfect matching. Okay. So there are how many perfect matchings are there for each of these vertices? So for first vertex, you have n options. Then for the second vertex, you will have n minus 1 options. So how many perfect matchings does this graph have? It has n factorial perfect matchings. And you might need to try all of them. So order n factorial time. And this you can verify. This is actually, so big O of n to the n or big O of 2 to the n log n. So this you can see that all these are same. So exercise. So this is I just wanted to do a survey that, okay, all these are the running times that we'll see somewhere in the course, and just to go through them so that, if you see them, you would have the feeling that you have seen them before. And now we will, so this was basically the second chapter of the book or third chapter. So now we'll go to the next chapter. Yeah, I think this was the second chapter of the book. And now we'll go to the third chapter, which is about graphs and graph algorithms, some basic graph algorithms. And so for that, we will first just refresh some very basic graph notions. So I'll just write them down and you can, so what is a graph? A graph is just a pair, like a tuple, v comma e, where v is set of vertices. I'll just write vertices instead of set of vertices, just for time. And e is a subset of v cross v called edges, right? And you have directed graphs also, where the order matters, and then you have undirected graphs where order does not matter of an edge, right? You have concepts of adjacency, neighborhood. Again, so this you will need to refresh if you are not familiar with these terms, because these must have been taught in discrete math course. Okay. So, and we'll be using this. So NV is set of neighbors of V. Then N, this is NV union V. And S is equal to union V belongs to S N of V, set minus S. And N, okay, so this is They might look similar, but this one is normal bracket, this one is the square bracket, is equal to n of S union. Okay. So this is the terminology that we'll be using. And then some examples of graph you already know, like social networks, transportation networks, etc. You'll need the concepts of path, cycle, trees, rooted trees. Okay, connectivity. As I said, like, connected graphs and complete graphs are different, so don't confuse the two. And distance. So these are the basic concepts. So you just need to brush up the definitions if you don't remember them already. And you can go through any discrete maths book, or even this book actually mentions these things, Klein-Bocardus. So you can just go through that. Okay. Okay, good. So now graph connectivity and graph. So let's look at some graph connectivity problems. Or one basic problem, in fact. It's called ST connectivity. Okay, so what is the ST connectivity problem? Input is, yeah. Is there okay, no. Maybe the phone got like, yeah, automatically or something. All right. So input is G, V comma E, and sometimes we'll also say V of G to be set of vertices of G. And similarly E of G, set of edges. So we'll use that. And some ST are given, belong to V, and output is, or question is rather, so it's a yes no kind of problem. So question is, does there exist a path from S to T in G? Okay, so this is the question. So there are two natural approaches to solve this problem, which are called breadth first search, breadth first search, or BFS, and depth first search, or BFS. Okay. So these are the two basic approaches that we'll be looking at. So, okay, so how do these approaches work? So let's look at BFS first. Okay, so what do we do in BFS? So we start with S. So S is our starting node. We look at all the neighbors of S, which are at just distance 1 from S, right? So this, we first visit all the neighbors of S, and then so this is one layer, okay? Then what happens? We look at their neighbors. So we layer the graph. We go like, from inside, we go just one step, then we go another step. So we look at all their neighbors, which are, of course, not neighbors of S. Yes, there can be this guy, maybe this guy does not have any neighbors. Maybe this guy has 3 neighbors, this guy has many neighbors, okay? So now we got another level. Okay? And then, so on we proceed, right? And then we can go from here to here, maybe from here to here, maybe from here to here, and so on. And then let's say that's where the algorithm finishes. So this is the idea that we do, that we look at S, then we look at its neighbors, they become the first layer, then we, how to implement it will come later. But right now I'm just giving you the idea of the algorithm, that what does the algorithm do? Algorithm starts with S, then it goes first layer, second layer, and so on. Okay. So let's just formalize it a bit. That L1 is neighborhood of S. Okay, so I'll start using or try to start using the like script small s instead of just writing a small s because that might be confusing. So let me try to write like this. Okay. So neighborhood of S, because S capital letters are generally used for sets and small letters for vertices. So just to be careful. And what is Li plus 1 is equal to neighborhood of Li. And let's say L0 is equal to just S. Yeah. And neighborhood of Li minus sub union of 1 less than j less than equal to I Li, right? So what does this say? That what is going to be the first layer? The first layer is going to be neighborhood of S. And now you have reached to some ith layer. And what is going to be I plus 1th layer? Neighbors of Li which have not already come in any other layer. Right? Is the definition clear? That how this layering works.
Sir, in the union, there should be LJ, right?
Sorry?
In the union, there should be LJ.
Oh, yes, you're right. Yeah, thank you. Okay. So what you do, you take the union of all the layers that have been covered inside and you minus that because you don't want to include vertices from there. You just want to take new vertices. So that is why you take these neighborhood of Li and you remove the vertices which have already occurred. Okay. So there is this observation that so what is the first layer? L1. L1 has distance exactly 1 from S. So distance, again, minimum number of edges to go from one vertex to other vertex. I'm just repeating it, but like, yeah, you can, I'm not going to write it down. Okay. So let's say that observation is for any, or it can be a lemma also, I greater than or equal to 1. If it is too easy for you, it's observation. Otherwise, you can prove it also. For any I greater than or equal to 1, Li consists of all the nodes at distance I from S. Okay. And if a vertex V does not occur in any layer, then there is no path from S to V or V to S, whatever. Since we are dealing with undirected graphs right now. Yeah, so unless we specify that the graph is directed, the graph is going to be undirected. Okay, so this, if it is easy to see for you because from S you start and the first layer is distance 1 and then you can, okay, so instead of observation, if you want to make it a lemma and if you want to prove, you can prove it by induction. And so first part will be by induction and then second part can be by contradiction. That suppose that there is a path from S to V and then V does not occur, or basically then you can say that V will occur in some layer because then the path will have certain length and then the first part will contradict that V does not occur. So you can think about it, and this is the basic thing that these things will occur. If there is a vertex then which is connected to S, then it will occur in some layer of. So these L1, L2, L3 are layers. I think I used that term before also, but if not, I'm saying it again. Okay. So there is another concept related with this breadth first search, which is BFS tree. So you see this thing, actually you can make it a rooted tree. So what do you do now? You start from S. Okay. And now you look at all the vertices which are at distance 1 from S. So suppose these 3 are the distance 1 vertices. And then you look at their neighbors, and that becomes another layer. Then you look at their neighbors. Suppose there is no neighbor for this guy, and so on. Something like this, let's say. So this way you can, so this is layer 1, this is layer 2, this is layer 3, this is layer 4, and so on. All right. So now the question is that, so these are the edges which are being selected, but there can be other edges in the graph, right? So it might be that we started with S. These are the vertices. So this is some V1, V2, V3. There might be some edge here, right? There might be some edge here. Or maybe this vertex was adjacent to this vertex also. Or let's say not this way. You will have to think about why I'm not doing that, but fine. Okay. So suppose this vertex was adjacent to this vertex also. But this one got discovered first, right? So because this is at a distance 1 from there, so we won't put that vertex again with this vertex, okay? Because we want a tree. We keep adding edges. Okay. So we keep adding edges one by one so that, like, they are not going to form a cycle. So we now add edges only if the vertex is not previously discovered. So that's how we get the tree. So we start from S, we get this first vertex, then we go to the next vertex, and it has not already been added. So first we have to exhaust all the neighbors of S itself, right? So first we look at this edge, it gets discovered through this edge and this edge and so on. Now, if we go to this vertex V, it has these neighbors 1, 2, 3, 4, 5, 5 neighbors, right? But 2 of them have already been discovered, or they have already been added to the tree. So we will not add them to the tree. We will not add these red edges to the tree. We'll only add the new, because these 3 vertices are going to be the new vertices, so we'll add these 3 edges. So there can be other edges in the graph which do not get added to this BFS tree, right? But there is some property about that. Can there be an edge like, let's say, from V to here? Or from, let's say, from here to here? Can this happen?
No, sir.
No, sir.
Why this would not happen?
Sir, then it will come to the L3 layer instead of L4.
Exactly. Or in the earlier case, it will come to L2 instead of L3. This one, right? For this one, this vertex will now come to L2 instead of L3, right?
Yes, sir.
Okay, good. So let's write it as a lemma. And what will the lemma say? The lemma say that let T be a BFS tree of G. Sorry. Of G, and let XY be in VG such that xy, the edge. So also I'll sometimes use xy like this even for undirected edges, but I mean there is no order, right? If the graph is undirected. So just for, because I don't, I might forget making curly braces sometimes. So it's fine. Instead of a set, I might use a tuple. So let such that xy belongs to EG, okay, and x is in Li and y is in Lj. Then what can we say about I and j?
The absolute difference is not greater than 1.
Right? And what is the proof? Suppose the absolute difference was, so proof if by contradiction. So suppose I is less than j without loss of generality. Loss of generality. So let's say j is greater than I plus 1, and so of course if I is less than j, then x gets discovered first. So x's neighbors will be considered for Li plus 1. So we'll get, and of course since y is not in that, and y is also not in L. So either it will come in Li or Li plus 1. Y belongs to Li or Li plus 1. If y does not occur before, which is a contradiction. So you can fill in the gaps, but this is essentially the proof that if suppose the distance was 2, then you would consider this vertice's neighbors, and then this vertex would come one layer above, right? As some of you mentioned when I asked this question. Okay, so this is one very important property about BFS tree that we'll be exploiting in some applications and so on. And this is something to remember all the time, that whenever you have a BFS tree, the graph edges which are not in the BFS tree. So BFS tree edges already are, of course, between immediate layers. But even if there are graph edges which are not in the BFS tree, can either be in the same layer or can be across just like one layer. They cannot jump. There can be no jumping edges. Okay.
Sir, in the proof, we'll have to consider for Li minus 1 also, right? Like y belongs to Li or Li plus 1 or Li minus 1 also. It could be the parent of I in the BFS tree of X.
So I have supposed I less than j, right?
Okay, right, yeah.
So, right? I mean, one of them has to occur first.
Yeah.
Okay, good. So, all right. There is another concept of connected component of a graph. Right. So, and basically what you'll see, so that you can recall from whatever that connected component is such that there exists a path between every pair of vertices between the component or in the set. And then what does the BFS tree? BFS tree contains exactly those vertices which are in connected component having S. Okay, good. So, and if we know all the vertices in a connected component, then of course we can answer this question whether if we know all the vertices in a connected component containing S, then of course we can solve the ST connectivity problem. We can just see whether T belongs to that connected component or not, right? So let me just write that down. If we know connected component containing S, connected component, CONCOM is the short form I'm going to use, containing S, then we can solve the ST connectivity problem by just asking whether T belongs to this set or not. Okay, good. So what is a generic way of getting a connected component? So what is the generic algorithm? So this is going to be a more abstract algorithm, but connected component, let's say, is initially just S. And while there exists some V such that V belongs to, let's say, neighborhood of C, right? So this neighborhood of C does not include C by definition. You can check it above. Then we make it C is equal to C union V. And then we return C finally. Right? But this is a very abstract algorithm. So what does this algorithm say? That, okay, initially we have S. Whenever we get a new vertex, which is outside the current set, such that it is a neighbor of any vertex in the set, then we just include it in the set and we grow the current set. And when we finish up with all the vertices, when the while loop finishes, we get out of the while loop and return that current C. And this will give connected component containing S. Okay, good. So now the question is that, okay, this is one way, but this is not a very precise algorithm. This just says if there exists V, but we need some ordering, right? So this is too generic. We need some ordering. And BFS actually gives this ordering that, okay, first you consider the vertices which are, at layer 1 and so on. And then another way is to do DFS, right? So DFS, what does DFS do? So DFS basically goes from one vertex to some of its neighbor, and then it will not care about other neighbors of the first vertex. It will go to some neighbor of the second vertex, and it will go down, and it will go down. It will keep going down till it can go down. So that's why it is depth first search. And then when it finishes that, okay, now there is no neighbor of this guy which has been not been. So maybe this guy is neighbor to somebody up, but that guy is already visited. So you ignore the guys who are already visited, right? Because then there is no point of visiting them, just like before. So you always try to find new vertices, and whenever you find some new vertex, you go down. Now there is no new vertex to be visited from this guy. So you come up, you see, oh, can there some other new vertex be visited from here after coming one step up? Then you say, okay, maybe I can. Okay, fine. Maybe this guy was also adjacent to this, but you would not have considered it at that time because you were going down. Now, is there some vertex which can be visited from here? No. So you go up from here again. Okay. Then is there some vertex here that can be visited? No. Then you go up. Then again you see. Then again you see. Maybe there is nothing. Maybe there is something now. And so on, right? So that is how you do this. So let's just write this in a more precise way. So this algorithm DFS will have a global variable for a set called R, and so let's write DFSU. So it takes as input. So this is a recursive algorithm. It takes as input a vertex U, and what does it do? Mark U visited. So I could have written like, something like this for BFS also, but using similar things you can write. That is simpler than this. Add U to R. So this R is the global variable. And for each V in neighborhood of U, what do? If V is not visited, then you do a DFS V. Okay. Then you end if, then you end for. So this is the algorithm. What does it say? You go to a vertex U that is not visited. You add it to visited. So you mark it something. Okay, you mark it like with a circle. Okay, this is visited. It's then you go to its neighbor. Okay, and when you go to its neighbor, you call the algorithm again. So you will not go to another neighbor first. So suppose it had another neighbor here, but you will not go to that neighbor first. So what happened? You came here. Now again you start with this procedure with this vertex. Let's say V1. So then you start with this vertex. Then again it will mark V as visited. It will circle this and add this vertex to R. And then again for some vertex it will start the algorithm again. And then when it will finish all of this, then it will start with another neighbor of U. Okay. So first one branch has to finish, and then it will come up when all the vertices have been explored, and then it will go up. So is the algorithm clear at least? That what does the algorithm do? Any question about the description of the algorithm?
What is R here?
Sorry, I could not hear.
R.
Yeah, Vijay, can you ask again? Sorry, I could not hear your question.
What is R here? R.
Okay, so R is the set of visited vertices, basically, the vertices which have been explored.
We are asking it is visited. Again, we are adding it to R.
Why we are adding it to R? So R is just a set. I mean, so you are marking a vertex visited. Also, I mean, it's a similar thing. Fine, you can add it to R so that. Okay, so why we are adding it to R? A simple answer can be that it later you can be if you need some vertex to check whether it belongs to the set or not. So, for example, ST connectivity. If you want to solve using this procedure, then you initiate with R is equal to empty set and do DFS S and then check whether V belongs to R. So, I mean, also you can see whether V is visited or not, but then again, you have to traverse. Now you are just making a set. It will make it easier in the set to search for, some vertex. There's no other, of course, you are marking it visited. It is, slightly more work but for later searching, it is easier. That's the only thing why we are maintaining this R. Sorry, whether T belongs to R. Because we are solving ST connectivity. So now just you have a set. Instead of going and seeing which vertices have been marked, you have a set where you can find. I mean, it's just that. It's like just more cleaner way of looking at things. Okay, any other question about the algorithm? Yeah. Tell me, Vijay.
Sir, can you scroll up to generic algorithm?
Sorry?
Scroll up to the generic algorithm.
Okay, sure.
Okay. Sir, okay, I got it. Okay, sir.
Okay. Good. Any other questions? Okay, so just like BFS, we can also have this DFS tree also, and that is in the same way that I was drawing. That you are at S. Sorry. Then you go to some of its neighbor, you go some of its other neighbor, and as you keep discovering and adding these edges to the tree, whenever something new gets discovered, only then you add that edge to the tree. Okay. And then you go down, okay, as much as you can go down, then you go up, and now you saw that, okay, there can be edges which can be like this, can be like this maybe, right? But then you go up, then you go like this, maybe you go like this. Okay, so let's not kill the layers, by drawing in a bad way. So, right. Oops. This can happen. This can happen. And then finally you can go up and then do this. So now the question is, just like in BFS, we saw that the edges can only be in immediate layers. Here the edges we saw that can be like this, can be like that. But can an edge be like this? Or like this?
No, because then that particular node will have to be like below.
Yeah, that particular node will be discovered and it will come under this particular subtree, right? So let me just end with an observation and then another similar lemma as we had for BFS. So for a given call of BFS U, okay, all the nodes that are marked visited after the recursive call has been made and before it finishes are descendants of U. So this you can verify that if you make the call for U here, all the nodes that will be discovered will be in subtree of U, subtree which will be rooted at U, and it cannot go above because that's how the you connect this DFS tree. So this is an observation, and using this observation, we can prove a similar lemma like BFS. And what does the lemma say? Lemma says that, again, the language is similar. Let T be a DFS tree of G and XY be in VG such that XY, let's say, is not a tree edge. Okay. Then one of X or Y descendant of each other. So here these edges are not possible because this guy is not descendant of this, or this guy is not descendant of this, or the other way around. So these edges are not possible. And how do you prove this lemma? So I'll quickly give a proof. Okay, so proof is, so without loss of generality, let's say U be visited first. Okay, so now U is visited first, but xy is not explored, sorry, x is visited first, not u. X is visited first. So xy is not explored because otherwise y would be visited first. Sorry, xy is not explored. Yes, because if xy was explored, then y would be marked visited, and then this edge would be in the this thing in the tree. So if xy is not explored, then so you first visit x. Let x is here, and then you have the edge xy, which is not a tree edge. So this is not a tree edge. So if it was a tree edge, then xy is not. If xy was explored, then y would be marked visited. So y is not marked visited. In this thing, right? And y is not marked visited, so xy is not explored. That means y must be okay. So let it say this way: y is not marked visited. I don't want to say that. What I mean is that the edge xy does not get explored. Why it is not in the tree is because it does not get explored. So this is why. Sorry, I'm in a hurry, and that is why I'm making these mistakes. So because I don't want to go too much of time. So why this edge xy is not in the tree, and why it is not in the tree? The only reason can be that y is already marked visited, right? So if y is not visited, then we will do this DFS y, and then we will mark y as visited. So the only reason why this can happen is that when this edge was considered, whenever this edge xy was considered, y is already marked visited, right? So xy is not explored, then y must be marked visited. But y was not visited before x was visited by our assumption. So that means y is visited after the procedure was called for x. And that would imply that y is descendant of x from previous observation. So what happened that, okay, we came to x first, that we know that, okay, y was not visited before, right? And then we know that this edge was not added. That means what happened beforehand is that maybe some guy, some other guy or whatever saw y. But then y has to come under the tree of x, which is what the observation says. And that is why y has to be a descendant of x. So this is the thing that which just says that you cannot have these cross edges between different components of the or different branches of the tree. So in BFS, you cannot have the edges between layers which are more than 2. There's a difference of more than 2. And in DFS, you cannot have edges between different branches of the tree. So this proof, I might not have done it in the best way, but if you go through it, you can verify that this is correct. This is slightly a bit tricky, so to say, not as tricky also, but you can see that how to do it. Okay, any question about this proof? Any quick questions? No questions? So what does the proof say? Without loss of generality, let x be visited first. Now, why I'm saying xy is not explored? Because xy is not a tree edge, which is what the statement of the lemma says, that xy is not a tree edge, right? So xy is not a tree edge. Okay, and nobody told me that this is okay. Nobody's paying attention. So xy is not a tree edge. So xy is a graph edge, but it is not a tree edge. Then this will happen. So xy is not a tree edge. Why xy is not a tree edge? Because then y must be visited. Because if y is not visited, then xy has to be a tree edge. Now, why is not visited? Because it got visited
Sir,
in this call.
was it not denoting that x comma y is an edge in the graph?
Yes, that is there here.
So such that xy belongs to et. Okay, so eg. Yeah. Okay.
Yeah. Okay. Yeah. Sorry. Yeah. So good. I had forgotten to write that one thing. So let's write it this way. XY is belongs to EG minus ET. Okay. There I had said just XY is in VG. They are just two vertices, but fine. So it is an edge which is in G but not in T.
So do we really need that condition of not ET? Like, even if it is,
even if it is there, then also you can do that.
Then
yeah.
X or Y is descendant of each other.
They are descendant because that is just in one step you can do. Yeah, definitely. This is just to make this proof simpler so that, yeah, it's. Any other question? Like, yeah, I can take like 1 more minute. So please ask if you didn't get, because I am like, yeah, I was sort of, I should not have been in that much hurry about this proof, but okay. Yeah, you can figure it out. It's not very hard, but just the takeaway is that how the edges look like in BFS and DFS. That is going to be the takeaway. Okay, was there something in the chat? Sorry, so please unmute yourself and ask questions. So this was long ago. Avdesh, did you ask something? And oh, I less than J. You were answering a question of your class.
Yes, sir.
Yeah. Also, please don't call me sir. Like, you know, try to call me Ashutosh. That is, yeah. And okay, so we'll stop here, and thank you for coming today, and we'll see you guys. I'll see you guys on Tuesday now. Okay. So thank you. If you have any questions or whatever, you can ask it in Piazza, and yeah, hopefully somebody will answer it there, or you can ask it in the next lecture as well. Thank you.